My first story is about reionization in the universe. And reionization is this period very early on in the universe that's not very well understood. And basically, after the Big Bang, the universe was ionized, meaning there's um, so much energy filling space that atoms didn't exist. You had protons and electrons. And as the universe expanded and cooled, those atoms did form. So the protons combined with the electrons to form hydrogen atoms. And over several hundred million years, not much happened. The universe still expanded, but we think that stars weren't born until close to a billion years after the Big Bang. And so the universe was relatively dark. But once the first stars started shining, the intense amount of UV radiation from those stars started to reionize or to blow to the ultraviolet radiation would split the electrons from those atoms again. And so that's what reionization means. And today, when we look out into extragalactic space, the space between galaxies, we find ionized gas, meaning today much of the universe is actually reionized. And so this period between before reionization, when everything consisted of atoms, and then after the period of reionization, when everything consisted of basically protons and electrons, is of intense interest to astronomers because it's too far away or too far in the past for current telescopes to really study. But there's probably a lot of interesting things that are happening. It's the first stars, the first galaxies, the earliest quasars during that period. So there's a lot of interest in understanding this particular period after the dark ages of the universe. And I want to remind you that when we look out into space, we are actually looking back in time because it takes a finite amount of time for light to travel and to get to us. So, for instance, when we're looking at the sun, that's about 8 light minutes away, meaning we're seeing the sun about 8 minutes in the past because it takes about 8.5 minutes for the light from the sun to get to us. Similarly, when we look at the Andromeda Galaxy, it's about 2.5 to 3 million light years away. So we're seeing it that many years in the past. When we look at a very distant galaxy, um, almost 13 billion years in distance, we're seeing it that far in the past. And then finally, when we look at the glow from the Big Bang, the cosmic microwave background, we're literally seeing light from that far in the past. So here is another diagram where we're looking back in time and also deeper into the past. So the Big Bang is up here, and the present is down here. And here we are as astronomers looking back into time. And so we believe the epoch of reionization is around 400 million to about a billion years. And this period turns out to be the galaxies and the stars are so faint that they're really beyond the capability of current telescopes, although the James Webb Space Telescope, which is supposed to launch in another 3 years or so, should be able to start sampling the objects in this period. And so our solar system doesn't form until 9 billion years after the Big Bang, and here we're talking about objects at least a billion years after the Big Bang, or no older than a billion years after the Big Bang. So what happens during reionization? Well, space is filled with neutral gas, but then you started having these massive stars that put out lots of ultraviolet radiation. They also explode in supernovas. So all the UV and the winds from the stars and from the supernova basically start to excavate into the gas. So this is a computer simulation showing the expansion of these ionization regions. So the gas isn't going away, but it's basically turning from neutral gas, which is this dark stuff, to completely ionized or plasma gas, which is the blue. And the red is the regions that we call ionization fronts. So these are the areas where the UV radiation is basically expanding out like a bubble, slowly eating away into the neutral gas. So we have simulations of what we think is going on, but we are definitely interested in trying to probe this region. And it turns out that even though telescopes can't really directly see it, there are tricks. And one of these tricks that allows us to observe close to this stage of reionization is the so-called Hubble frontier fields. And the idea behind this goes back to the Hubble Deep Field. You might remember seeing pictures of this from 20 years ago, where the Hubble Space Telescope stared at a patch of sky for hundreds of orbits, and ordinarily, what looks like an empty patch of sky ends up having tens of thousands of galaxies, and the deep field has been repeated in different places. And when Hubble gets updates to its instruments, they acquire a new deep field because the new instruments can see deeper or are more sensitive. Um, and so this brings us to the latest version of the Hubble Deep Field, and the goal of this is to look as deep as possible before the launch of the James Webb Space Telescope, which would allow us to really directly view those very distant galaxies during the time of reionization. And the trick that they use is to use gravitational lensing. And so it turns out that light responds to gravity. So if you have a very massive cluster of galaxies, the the gravity from this cluster can actually bend the trajectory of light rays. So you can actually amplify, like a lens, a more distant cluster of galaxies that is much further away, and you can see it from the Earth. Whereas ordinarily, if this wasn't in the way, this would be very, very difficult, if not impossible, to see. And we find lots of examples of gravitational lenses where we have a foreground galaxy. That's what these center objects are, this yellowish and whitish object. And we find that they can be surrounded by these arcs of bluish light. And what we're seeing is a background galaxy who much further away than this foreground galaxy, and the light is being distorted by the gravity of the foreground galaxy, just like a lens would. And an example of this, you can try this at home if you have wine glasses, is to take the bottom of a wine glass and to point it at a single light source, like a candle here, and depending on your exact orientation, you can see this point break up into like a ring or an arc. So this is a similar phenomenon, not exactly the same. And so the goal of the Hubble frontier fields is to pick clusters of galaxies in 6 particular patches in the sky and to observe it extremely deeply, and using these clusters and the gravity of these clusters as effectively zoom lenses so that you can observe even more distant galaxies. And so some of the first results from this was announced in a paper that's currently under review, and I think it will be published pretty soon. And the Hubble Frontier Field started in 2014, so they've only observed 3 clusters so far. So Abell 2744, MAC S0416, and MAC S0717. And there are 3 other fields that are currently being observed. And so when they have observations from all 3 fields, you'll be sure that they'll be redoing this analysis. But here are the 3 fields, and you can see there are lots and lots of foreground galaxies. And if you look really closely, I think it's really hard to see here. You might even see hints of arcs that are really faint. You'd have to zoom in to really catch them. Here's a zoom in to Abell 2744. So again, lots of foreground galaxies, and again, very faint background galaxies. And in all these pictures, every single bit of light, every single smudge is an entire galaxy. So we're not actually seeing any foreground stars. And finally, here's the last field. And again, if you look really closely, there you start seeing little, very faint bluish arcs. So what do they find? They discover about 250 new dwarf galaxies that are some of the furthest ever observed. So they're actually finding some of the most distant galaxies from these super deep fields where you're using the gravitational lens to amplify the light from those very distant galaxies. And these galaxies, we're seeing them anywhere from about 600 to 900 million years after the Big Bang. So these are extremely young galaxies. And what they are also finding is that the ultraviolet radiation from the stars in these galaxies are enough to contribute to reionization. And so one of the things that you can do is that you can take the counts of these galaxies and figure out a galaxy distribution function. And so these red circles from this paper, these red circles are from this current paper, and then these squares are from other previous papers. And what they're finding is that, and this is kind of a confusing plot that only makes sense to astronomers, but the brightest galaxies are down here, and the faintest galaxies are at this end. And so you would, when we look out into space, we find fewer big bright galaxies and more smaller faint galaxies. And so when people observe galaxies, they'll tend to find a bunch of dots that tell you how many galaxies are found at either the big galaxies or the small galaxies or the galaxies in between. And then you can draw a line to describe mathematically how many galaxies exist based on your observations. But the problem with the points at the faint end is that people weren't sure whether they were seeing all the faint galaxies. And so you can still draw this line through the squares, but perhaps there are more galaxies that you aren't seeing because they're so far away. And so what this new paper is showing is that there does indeed appear to be more galaxies than, or the faint galaxies than we're seeing in the earlier surveys. And so we are seeing the hints of reionization.